welcome to do so. If you thank you. Goodbye.
Um, is this already supposed to be recording? Because it might be pretty long if it's been
Yeah,
working.
it is recording. Yeah.
Okay. I was just wondering because it'd be like 30 minutes longer if someone's trying to review the recording.
Yeah, because I signed in early because there was a student who wanted to talk to me.
Oh, okay.
Some questions.
Good morning.
Hey, Michael.
Hi. Sorry about the awkward introduction there. Nice to meet you.
Yeah.
Yeah, well, I guess the first question I had is just kind of over classical versus quantum operators.
Mhm.
So looking at the book, like for example, for momentum, right, it's h bar over j and then partial derivative of in respect to x, right? But I'm not really sure what goes in the arguments. Is that the wave equation? Is that
Yeah.
okay?
So,
Okay.
To answer your question, ultimately these are postulates that you make in quantum mechanics to
Mhm.
explain experimental data. So in physics, the touchstone is always do your predictions agree with experiments. So constructing those operators, you get results which agree with experiments. Now you might ask, of course, how did physicists come up with such weird postulates, right? So
Mhm.
over there, they had the benefit of having the spectroscopic data, and that led Bohr to make that weird assumption that the angular momentum has to be in h bar, right? So when quantum mechanics was developed by Schrodinger and Heisenberg, they're not working in absolute darkness, right? I mean, they knew what the experimental data was, and they had this pre-quantum mechanical quantum physics type hand waving arguments.
Okay.
And then when Schrodinger constructed his wave equation, he saw that, okay, if you define the quantum mechanical operators which are analogous to classical quantities, you come up with an equation which is a more satisfying way intellectually of explaining the Bohr postulates in terms of the de Broglie wave function. So you really can't derive the Schrodinger equation. I kind of pretended to derive it, but that's based on definitions of these quantum mechanical operators, right, which were pulled out of thin air. So
Well,
I
remembered seeing in the book that you can only really use that for the hydrogen atom because it's the simplest. That you need more like complex models to represent wave equations for atoms beyond that. Is that
right? So even in classical physics, you cannot exactly mathematically solve even a three-body problem. Okay, you can solve a two-body problem using Newtonian mechanics very well. Okay, but the moment you go to even a three-body problem, you can solve it approximately on a computer, but there's no analytical solutions. Okay, the same thing is true in quantum. So in quantum, there's two ways of approaching it. When you have a more complex atom, you can approximate the effect of all the other electrons. You just focus on one electron at a time, okay? And then you say that all the other electrons kind of effectively modify the nuclear potential, okay? It's called screening. So, the positive charge in the nucleus is kind of shielded by all these core electrons and every other electron other than the one that I'm focusing in. So you define not a Coulombic potential, but some sort of a effective potential, taking into account the screening effects of the nucleus by all the other electrons except the one that I'm trying to solve for. Okay, so that's one approach. A more elegant approach is to construct what's called a many-body wave function, and I kind of hinted at that last time. Remember, we said that if you have two identical electrons, and of course all electrons are identical, at quantum states A and B, you can swap them, and then you get a minus sign when you swap them in the case of electrons, right? So similarly, suppose I have a complex atom like silicon with 14 electrons, you construct a wave function psi1 at A, psi2 at B, all the way up to psi14 at whatever it is, right? And then, so that's the way it's done, but you can't solve it analytically. You can do it on a computer very well.
Okay. So it kind of sounds to me like it's either, too complex to solve by hand or kind of an estimate.
Right.
Yeah. Okay. I just, I'm not asking for homework solutions, but I just in 2.10, which is assigned. I know, like looking at it's the normalization equation.
Can you briefly remind me what the question is? I can't remember.
Yeah, sure. Yeah. So let me go ahead and flip to it real quick. Okay. An electron is described by a plane wave function, calculate the expectation value of the function defined as 4 px, where p is momentum, squared plus 2p pz squared plus 7 me, where m is the mass of the electron, px and pz are the x and z components of momentum, and e is energy. Give values in terms of the Planck constant. Anyways, I was kind of looking through it, going about it. Let's see. Right, it seems like an average value problem. So
Right.
average value of any particle q is given by integral from -infinity to infinity of complex conjugate times q operator times the wave equation.
Not times. It's q operator operating on the wave function. So you're not multiplying it. Right?
Oh, okay.
Right.
Okay. I that clears a lot up actually.
Right.
Okay.
So
okay.
so you have those operators for p or e or p square or whatever.
Okay.
So you differentiate with respect to x or time or whatever on the wave function, and whatever result you get, you multiply that by the complex conjugate. But then the trick that you have to use for plane waves is, if you try to integrate from minus to plus infinity, you'll end up with an infinity over infinity. That's why you have to play this trick of minus L to L, a finite box. You'll see that the L squares the L's will cancel out in the numerator and denominator, and then you take the limit of L going to infinity. Okay, so you have to use that special trick only for plane waves.
Okay. Yeah. Okay, that actually makes a lot more sense, because I was kind of looking at it thinking there's no argument in this partial derivative. Right. So yeah, I was like, what do I do with that? So, and also just kind of wanted to confirm. So on the de Broglie and Planck relationship, so there's this V quantity, which somewhere in the textbook, it seems to be velocity, somewhere it's frequency, somewhere it says it's frequency of radiation. Are those all kind of the same?
No, they're not. So if you look at the exact symbols, when you have frequency, it's not V. It looks like a V, but it's actually the Greek symbol nu. Okay.
Okay.
Yeah. So yeah, we use different. Yeah, there's only so many alphabets, so we had to kind of use the same kind of alphabet. But if you look carefully, the shapes are slightly different. Okay.
Okay.
Yeah. So if it's a capital V, that's generally potential energy. If it's a small v, then it be velocity. And then the other thing that looks like a Greek V, that's actually the letter nu, and that's frequency.
Okay. Gotcha. All right. Okay. So I'm kind of getting it.
Okay, good.
Yeah. All right. And I had a couple of other questions on the atomic spectra section. Kind of trying to formulate what I'm trying to ask here. So I know there are discrete energy states, right? So it seems to me that whenever a electron is excited so that it goes from one energy state to the other, that it gives off some frequency of light.
No, it absorbs. It absorbs. Yeah, but when it goes from a higher to a lower energy, it gives off a certain frequency of light.
Right. Okay. Okay. Yeah. So either absorption or emission based on that. Okay. Okay. I also wanted to ask about probability density functions. So it seems to be that it's px equals integral of the magnitude of the wave equation. Is that?
No, magnitude squared.
Magnitude squared, right?
Yeah.
Sorry, I just misspoke there. Okay. And then also, because I mean, I just took 351K, and they kind of hammered the point in that class that for probability density functions that the integral is always going to be equal to 1.
Yes.
Right.
Yes.
But I kind of looked through the book, and so And I know that that means that it's normalized, but it seems like there's some examples where it would be non-normalized. Is that, am I
Right,
just
you should-
making that up? Yeah,
No, they'll
Right.
always be they'll always be normalized. So if you
right.
integrate psi magnitude square from minus to
Mhm.
plus infinity, it
Mhm.
should always be equal to 1. Okay.
Mhm.
So if it's not 1, that means you just scale the thing up or down to make it integrate to 1. Okay.
Okay,
So it's the same
Right.
as in 351K. Yeah.
yeah, okay, perfect. So, all right. I don't really think I have any other questions at the moment.
Okay.
Nice to meet you.
Sure.
Uh,
Yeah.
Yeah,
It's terrible having to do it through Zoom, but yeah.
yeah,
hope,
it is.
I hope it's not too bad, but yeah.
Right. And also something I want to let you know real quick is that I'm in it's the Talent Success Program. I don't know if you've
Okay.
heard of that or not, but
No.
basically for helping students who have kind of fallen behind or just want sort of extra help to kind of
Okay.
get ahead and stuff like that. Anyways, point is that I have to meet with you and
Okay.
well, all my other professors really once a month starting
Okay.
after the first midterm. So
Okay.
just kind of wanted to let you know that.
Sure.
So,
Yeah. And if you have questions other than the office hours, just call me on my cell phone. Okay. So office hours are good, but if you have other problems that you need to talk to at other times, feel free to call me at other times also. Okay.
Okay, perfect.
All right.
Well, thanks. That seemed to
Sure.
answer a lot. So,
Okay. All right.
alrighty. Okay.
Actually, I was wondering if I could also ask a question about the homework problems.
Sure.
So on 2.6, where it's assigning C to the normalization constant,
Mhm.
I'm not sure if I'm just mistaking what it means for the normalization constant. Is it referring to the equation that
No, it
we
refers to the
find out in the wave function section of the lectures?
it's referring to the wave function. You don't normalize the equation, you normalize the wave function. Okay. So as I was just saying, wave function magnitude squared is your probability density function, right? And that should integrate to 1. So if the wave function is in terms of C, when you square it, you'll get C squared, okay? And then whatever the functional dependency is. So you integrate the whole thing, so you'll get C squared times something, and you set that equal to 1, and that way you can solve for the C.
Okay. But it's asking if it's possible for it to be a wave function. So are we just saying if it ends up just being like, I'm confused on why we would check if it's possible to be a wave function
Okay.
if it
Yes,
already
yes.
is set to C to a degree.
Right. So it turns out not all wave functions are valid wave functions. And interestingly enough, we've been talking about plane waves, right? And plane waves are actually not valid wave functions, because if you take e to the power I kx times e to the power minus I kx, that gives you a product of 1, right?
Yeah.
And then times c squared. So if you integrate that from minus to plus infinity, it'll never give you a finite number, right? Regardless of what the value of C is, it'll always blow up to infinity. So strictly speaking, a perfect plane wave cannot be normalized. It's that one special pathological case.
Okay. But like, so in the homework, one of them is just equal to C, which I feel like, sure, that makes sense. It's just a standard waveform constant. But
No,
then,
yeah.
but
If
then
that
one
can-
of them has like 2 values where they're supposed to be 2 different values at the same time. And are we supposed to just say it can't be 2 different things at the same time, so it can't be a waveform?
Exactly. And similarly, if it's a constant everywhere, that's also not a valid wave function, because if constant square, if you integrate that from minus to plus infinity,
It goes to infinity no matter where you're
right?
plugging it in.
So that's not
Okay.
a valid wave function. So always use the intuition that wave function magnitude square should be a physical probability density, right? And anything that doesn't make sense physically in terms of probability density is not a valid wave function.
And saying it's set equal to a value for all x is not the same thing as saying it is that value, correct? Like I don't want to, want to make sure that I'm not just setting the equation equal to something that it's not technically.
So that again, could you repeat that?
Okay, so 2.6a says that the equation, like I'm having a hard time remembering all the Greek variables, but I think it's like phi of x is equal to c for all x. That's not the same thing as saying the equation itself is c, correct?
Right. So you're just defining the function in that case.
Yeah. So in that case, it should be a potential waveform because it's still giving you values for every x and they're defined, right?
So I'm not, so you pretend that you've solved the Schrodinger equation for some potential, okay? And that was the solution that you got. And the question is that possible based on the physical meaning of wave function magnitude square being the probability density function?
Okay.
So I don't call it an equation, it's defining the value of the function. Good morning. So we're going to continue our discussion about band structures and then move on to concepts of electron hole pairs and things like that. So to quickly refresh your memory from what we discussed on Monday, we said that suppose you consider a single atom which has a 1/r type Coulombic potential. You can solve the Schrodinger equation and you get these various distinct eigenenergies, which are like the Bohr allowed energy levels and the corresponding wave functions, which are called eigenstates, or in the language of chemistry, these are also called orbitals. Next, we said that if instead of a single atom, suppose I take two atoms, say one located at this location over here, I'm showing the positive ion core, it has distinct energies, and then I take another neighboring atom and I bring them closer and closer together. We saw that the individual wave functions start overlapping in space, and then you have to construct either even combinations or odd combinations. The even combinations go down to slightly lower energies, while the odd combinations, which are known as anti-bonding states, go up to slightly higher energies. So the point was, if I take two atoms and bring them together, the original distinct energy levels split up into two energy levels, okay? By extension then, if instead of two atoms, suppose I have a large number of atoms, say of the order of the Avogadro number in a crystal. Here I'm not showing an Avogadro number, I'm showing about, say, 10 atoms. What will happen is this distinct energy levels will split up into 10 closely spaced energy levels, okay? And that's what I'm schematically trying to show over here. If n is very, very large, those closely spaced levels almost form a continuum of energies, and that's what's known as a band. Now, the width of the band, how much it splits up, doesn't depend on the number of atoms in the crystal or the size of the crystal. It depends on the separation between the atoms, or the lattice constant A. The smaller the value of the lattice constant, more the overlap, and more the energies will split up, okay? And then, depending on the number of atoms or the size of the crystal, I'll put that many states within that energy band, okay? And we also said that the lower lying bands, which at the core levels don't really play any significant role in semiconductors. The more interesting stuff happens in the highest, more or less occupied band, corresponding to the valence shell, that's known as the valence band. And then above that, you have forbidden energy states, which are called the energy gap. And then next excited state, which is generally almost empty, not fully empty, but almost empty, is called the conduction band. Now, above the conduction band, you have even higher lying possible states, but those are so high up in energy that they'll never be occupied. So all the fun stuff is with the valence band, the energy gap above that, and the conduction band. Now, what I also showed in this picture is, suppose I have a finite crystal made up of, say, what is it, roughly 10 atoms in this case, okay? You can think of that finite crystal itself as a quantum box, a particle in a box state, because to take electron out of it, out into space, into vacuum, you have to impart some energy to it, right? If I take electron in the valence band, you have to give it some energy to yank it out of the crystal. The energy of the vacuum is known as the vacuum level, and the convention is to set that energy reference to be 0. So with respect to that, the electrons in the crystal have a negative binding energy, and that's what keeps the electrons in place. Otherwise, you think that if you have a solid which is full of electrons, why don't the electrons spontaneously come out into space, into the air all around it? That's because they are bound by the nuclei in the crystal, okay? So at that point, then, you see that we have two types of quantum boxes, particle in a box state, okay? First of all, you have the 1/r type Coulombic box of the individual atoms, but then you put them inside this larger box made up of the finite crystal, okay? And we saw last time that anytime you put a particle in a box, when you introduce those boundary conditions, you introduce this distinct eigenenergies, all right? Now, one trick, mathematical trick that's used is, although the finite crystal corresponds to a finite box, that makes standing waves. So you take linear combinations, e to the power jkx plus another constant e to the power minus jkx, and that would be written in terms of sine kx, cosine kx. Those are the standing waves that we talked about when you solve the particle in a box. Now, the math becomes a little messy in terms of sine and cosines. People prefer to often work with the traveling waves, e to the power j, k, x, whatever, okay? So that's achieved by taking this finite crystal of, say, length L and just replicating it from minus to plus infinity. So you just map it onto another crystal between here to there, okay? And then you make another crystal. So you pretend that you're just joining these finite crystals from end to end over all space. So that mathematically now looks like an infinite crystal where you'll have traveling waves propagating all the way back and forth, okay? And you might say, wait a minute, I mean, that's a different problem, right? Well, it really makes a difference only at the surfaces of the crystal, where you have normally defects called surface states. As long as well inside the crystal, the electrons well within the crystal really can't tell what's really happening at the surface. So this so-called periodic boundary condition is a mathematical trick which makes the math simpler without changing the results in the inside of the crystal. It does change the results right at the surface, but those will treat separately. All right, so then what we said was, okay, let's now zoom in on the valence and the conduction band, and that's what I'm drawing down below, where I said this is a very, very key concept that I wanted to be super comfortable with, because unless you know how to read band diagrams, this course will not make any sense at all. Okay, so every single device, PN junctions, BJTs, MOSFETs, everything will be analyzed in terms of band diagrams. So please spend a ton of time, getting a physical sense of what the the simplified band diagrams mean. And it's actually quite straightforward. The two axes we said was the horizontal axis is position. So when the electron is at different locations in my transistor, say, that's my horizontal axis, the position. And the vertical axis increasing upward is electron energy increasing upward, okay? Now, electron and holes are sort of cousins of each other, if you will. So hole energies, it turns out, increase downward, while electron energies increase upward. Now, of course, energies of a particle have a kinetic energy component and a potential energy component. When I'm at the band minimum, denoted by E sub c, that's the minimum of the conduction band, that corresponds to zero kinetic energy. So it's only electron potential energy at that point, okay? And as I add kinetic energy, I move up in the band. Conversely, if I'm at EV, that's the top of the valence band, and I'm looking at holes, the hole only has potential energy. And if I move down in the band, I'm increasing hole kinetic energy. So that's really the only physical concept that you have to keep in mind. Okay, and everything else makes sense based on that. All right. So the first simplified diagram that I'm showing, of course, has flat bands, right? So what that means is the potential energy is constant everywhere. So if I write down my total energy E as a potential energy term, which if I have electrostatic potential V, which is a function of position R, the electrostatic potential energy would be the charge of the electron, which is minus Q times V of R, plus the kinetic energy, which is P squared over 2M. Now, P, we saw in the previous class, is the de Broglie relationship, H bar K. So if you plug that in, I get H bar squared K squared over 2 times the mass of the electron, right? Now, you'll notice that I put in mass with an asterisk because in a solid, the mass of electron gets modified into something called the effective mass. I'll explain that in just a second. Now, let's see what these two pictures then tell us. Okay, so if I go to this equation, as I said, if I'm at the band minimum, that corresponds to just potential energy minus QVR, or I can write that also as EC as a function of R, okay? On the right-hand side, I plot what's called a band structure. On the left-hand side, those are called simplified band diagrams. On the right-hand side, I show similar information, but in a different set of axes, and those are known as band structures, where I now plot electron energy increasing upwards, same as in the left-hand side figure, but the horizontal axis is no longer position, instead it is K. What is K? K is, of course, the wave vector. K is equal to wave vector, and we saw that's given by 2 pi divided by the de Broglie wavelength, and H bar K being equal to momentum. Physically, K is basically proportional to momentum or the velocity of the particle, okay? So if I now plot this quantity, total energy, as a function of k, of course, we saw there is a parabola, right? Because y equal to x squared is a formula of a parabola, okay? So in this parabolic band structure, if I now look at the k equal to 0 point, that corresponds to momentum equal to 0, or velocity equal to 0, or kinetic energy equal to 0. So k equal to 0 point must correspond to just the potential energy term. So that point corresponds to EC if I'm in the conduction band. Now we'll see in a second that in the valence band, you get an inverted parabola. So that point corresponds to EV. As I move up in the conduction band, in the simplified band diagram, that's analogous to moving up this parabola in the case of electrons, or down in the case of holes. So that's the correspondence. Now, the first diagram that I drew is very straightforward, and it's a horizontal band diagram, okay? So what that means is this EC is constant, meaning V of R is a constant, the electrostatic potential is constant. And we know from EMAG that the electric field E is given by minus dV dx or dV dr. So if V is constant, that tells you that the electric field is 0. So this band diagram that I just drew corresponds to the 0 electric field case. Now, that's not very interesting, of course. How would the band diagram change if there was electric field? Well, if it was a constant electric field, the bands would slope. Instead of having horizontal lines, you'll have slope lines, but the gradient is proportional to the gradient of the potential or the electric field. Now, which way does the electric field point? Well, since electric field is minus dV dx, and EC is equal to minus Q VR, in this case, it turns out the electric field will point this way. Why? Well, if EC is varying like so, that means the electrostatic potential is varying this way, right? It's increasing the opposite way, because remember, it's minus Q times VR. And then if I take the gradient, okay, a slope like this, minus dV dx will give you a slope like this, okay? And that makes perfect sense, because if I'm an electron over here at this point in space, can anyone tell me what the kinetic energy of that electron is? Anybody? If I'm at the band edge, say at this location, I don't know if you can see my.
The mouse doesn't show up on the screen, so I'm not.
Oh, it doesn't show. I see. Okay.
Yeah.
So if I'm at the band edge, we just said that the kinetic energy is 0. So if I'm at the band edge, the electric field, the kinetic energy is 0. It only has potential energy. The next question is, does that electron see any force? Is there a force on the electron? Well, in the first case, where the bands were flat and the electric field or force was 0, clearly the force, which is minus Q times electric field, has to be 0, right? On the other hand, in the case of a non-zero electric field, as shown in this case, there will be a force, and the electron will move in the direction opposite to the electric field because they have a negative charge. Okay. Holes, on the other hand, move in the direction of the electric field because they behave like positive charged particle, so they'll move in this direction. And you notice that as they move away from the band edge, they gain kinetic energy from the electric field. I'll show this picture again, in a cleaner form, 3 or 4 slides later on. Okay. Now, this is, of course, a case with a constant electric field. If electric field is constant, that means minus dV dx is constant, meaning it's a constant slope, and therefore the band edges are with a constant slope. Now, the most general case is the slopes themselves will vary with position in a device, such as in a PN junction diode. We'll see in chapter 5. You may get band diagrams like this. So at different locations, wherever the bands are flat, there's a 0 electric field. As bands start sloping, you take the gradient of that, and you'll get a spatially dependent electric field, and so on and so forth. Okay. So once again, stare at these band diagrams. Make sure that you understand what the axes are, and see which point corresponds to potential energy, which point how increasing kinetic energy of electrons and holes are represented, and so on and so forth. Okay. One final comment, as I said last time, is in these bands, the bottom of the conduction band and the top of the conduction band would be parallel to each other because it corresponds to the width of the band, which is a material parameter. That's why typically we will not show the top of the conduction band or the bottom of the valence band when you draw these pictures. the convention is to just show EC, which is the bottom of the conduction band, and E sub V, which is the top of the valence band, and plot those as a function of position. That way the figures don't get cluttered up. All right, so then we said that in terms of this energy band gap, you can distinguish insulators from metals and semiconductors. So if the band gap is 0, that is like a very good conductor, such as a metal. If the band gap is very, very large, you can't excite electrons from the full valence band into the empty conduction band. And just like a full water bottle or an empty water bottle does not give rise to any net water movement from one end of the bottle to the other, here also there'd be no net motion of electrons, even if you apply electric field. That's why it's an insulator. On the other hand, if the band gap is small, small meaning of the order of 1 electron volts or so, that's kind of what makes it a semiconductor, because now at room temperature, which is 300 Kelvin, the thermal energy of the electrons is given by something called kT. Now this K is not the wave vector K, this is the Boltzmann constant. So let me write it as K subscript B. So K Boltzmann times T works out to about 25 millivolts. And this is a number that will come up again and again when you solve problems. This is known as the thermal energy in the system, okay? So our physical interpretation of this is these electrons at room temperature are not going to be static. They are constantly going to jiggle around with an average kinetic energy given by kT. Once again, this K is not the wave vector K, it's a Boltzmann constant, times temperature in Kelvin at room temperature, which is 27 degrees centigrade approximately. You add 273 to that to convert centigrade to Kelvin, and plugging those numbers in, you get roughly 25 millielectron volts. Obviously, if you heat up a semiconductor, that number goes up. The electrons are going to jiggle around more violently. If you cool down a semiconductor, they become more sluggish. So what one needs to do is one compares the magnitude of the band gap with respect to this thermal energy kT. And if EG is not super large compared to kT, a few of these electrons in this full valence band can be thermally excited into the conduction band. In the process, they leave behind empty states, which behave like these positively charged holes. And what you end up with in the conduction band are negatively charged electrons, as I was describing. Okay. All right. So now I want to put this concept of holes on a firmer footing. We already mentioned on Monday that you could use this famous water bottle analogy, right? So the full valence band is like a full water bottle, which cannot allow any water movement from one end to the other, even if you move it around in the gravitational field. Empty conduction band is like an empty water bottle. Obviously, there'll be no water motion possible at all. Now then, you could take a few water droplets from the full bottle and move it into the empty bottle. So those droplets of water are like your electrons, which move down under gravity. But what's left behind are these air bubbles, which move up in gravity. Okay. Similarly, electron and hole energies point in opposite directions. So the analog of the water droplets are these conduction electrons, negative electrons in the conduction band, and the analog of the bubbles are the holes, the empty states in the valence band. Now, you might say, I don't like this concept of bubbles. To me, bubbles are not real. Only the water is real, right? So you can get the same results. In the case of this partially filled water bottle, you can map out the motion of these air bubbles, not by thinking in terms of the air bubbles, but all the other 99% space filled with the water, right? So if you monitor the motion of those approximately 99% or so of the water molecules, you get the same result as you'd get by just monitoring the motion of the air bubbles. But the question is, which do you think is going to be easier? Now, clearly, if you only have a few air bubbles, you're much better off just monitoring the motion of the air bubbles. So similarly, it makes sense to use this language of a few holes, even though you'd get the same result by just considering the motion of all the other Avogadro number minus a few electrons, okay? So that's why, bookkeeping in terms of a few holes in the valence band and the few electrons in the conduction band is a way to do the thing, all right? Now, when you plot the band structures, one finds, we saw that in the conduction band, you get a parabola like this, Ek equals h bar square k square. I guess I have it over here. So, okay. So E of k is p square over 2m. That's kinetic energy plus h bar square k square over 2m, plus, of course, whatever the potential energy is. So the potential energy point corresponds to k equal to 0, where the kinetic energy equal to 0. Now, in the valence band, one finds that you end up getting an inverted parabola. Okay, so I'm not going to go into the details of how that's done. The short answer is you put the crystal periodic potential into the Schrodinger equation, and you crank the machinery, and you get a whole sequence of solutions for the different states. Okay, some of them will curve down, and some of them will curve up. And it just so happens that in the valence band, it curves down. The parabola curves down, while the next highest conduction band states, you have a parabola curving upwards. Okay. If you take a graduate course in semiconductor physics, we'll tell you how these are calculated. Okay. Here we'll just take that as a given and see what the consequences are. Okay. All right. So the first consequence is, what is a velocity of one of these electrons at different values of k? Where we know that the velocity is the momentum, for example, is given by h bar k, and therefore the velocity will be given by v is momentum over mass. Okay, so that'll be given by h bar k divided by whatever the mass of the electron is. Okay, now let's see if I can derive an expression for the velocity in terms of this E of k. Okay, the way to do that is you take this E of k and you take the derivative dE dk. And if I take dE dk, what will I get? I have the h bar square k square over 2m. So I'll now get h bar square k times 2 over 2m, right? Because if I differentiate x squared, I get 2x. So if I differentiate k squared, I get k times 2, right? The 2's will cancel out. So I'll be left with h bar square k over m, right? Now, what is h bar k equal to? Well, h bar k is equal to momentum. So this works out to h bar momentum over mass. Now, what's momentum over mass? That's velocity. So therefore, that's equal to h bar times velocity. So therefore, velocity is nothing but, if I bring the h bar to the other side, it's simply 1 over h bar dE dk. Okay. Now, what does dE dk correspond to? I have some function E of k. What does dE dk physically correspond to, or mathematically correspond to? Anybody?
The change in energy.
Right. It's a slope, right? So the dE dk at different points will be whatever the slope of this parabola is, right?
Like the tangent of each location.
Right, right. So what you see is the magnitude of the slope is not constant. So at k equal to 0, what is the slope? Slope is also equal to 0, right? Therefore, what is the velocity? Velocity is equal to 0. Now, in this simple case, you could also have gotten the same result by saying that, if k equal to 0, momentum equal to 0, and sure, velocity equal to 0. But in just a few minutes, we look at more complicated band structures. And there you have to really use the more fundamental definition of velocity. This is sometimes called the group velocity of a wave packet, as opposed to the phase velocity. You may have seen these terms in physics 303K and L. So this is the group velocity, and that's given by 1 over h bar dE dk, the slope of the band structure. Okay, and you can see clearly as you go up in energy, clearly h bar k is increasing and the velocity is increasing because the slope is increasing. All right. Now let's go one step further and take the second derivative. So I've already taken the first derivative, right? So I've gotten dE dk was h bar square k over m, right? Now what if I take the second derivative, d2e dk square? What will I get? The k vanishes, right? And then you can invert this expression and you can write m, the mass, equal to h bar squared divided by second derivative of d2e dk square. What does d2e dk square correspond to, the second derivative? The first derivative we saw corresponded to the slopes at different points, okay? The second derivative, I don't know if you remember from your calculus classes, it corresponds to the curvature of a function, okay? So if you have a function that's more curved, the second derivative will be larger. If it's less curved, the second derivative will be smaller. So what this equation tells us is, or this equation rather, the mass of electron can be expressed as h bar squared divided by the curvature of the band structure. If the band structure is more sharply curved, the electron behaves as if it has a lower mass. If it's more gently curved, the electron will behave as it has a larger mass. Now, at this point, you guys should freak out. You know, electron is electron, right? I mean, it's a fundamental particle, and it has whatever mass it has, right? So what is this funky business about effective masses? Well, what the effective mass captures, and we'll explain that in greater detail next week when we start looking at transport, what the effective mass captures is these very, very complicated interactions of the electron moving in the periodic crystalline potential. So when these electron wave functions are moving in a crystal, clearly they're not moving in empty space or vacuum. They're moving in this environment of this periodic crystalline potential, okay? So under those conditions, one finds that the electron wave function is no longer written as a plane wave e to the power ikx, okay? Instead, it's written as a plane wave e to the power, sorry, jkx, let's be consistent, jkx, which is a plane wave in free space, but then you have to multiply that by another function, uk of x, where uk of x has a property that it has the same periodicity as the crystal. So if the spacing between this nuclei was a, clearly we'll have Vr plus A equal to Vr, right? I mean, if you translate by one lattice constant, you'll get the same value of the potential. So this uk of x plus A will be equal to uk of x. Okay, so this uk will have the same periodicity as the crystalline potential. And that theorem was given by a physicist called Bloch. So these wave functions are known as Bloch wave functions, okay? So physically, what I'm saying is, instead of a plane wave, as in free space, you now get a plane wave which is modulated by a function, some complicated modulation, this uk of x term, which captures the interaction of the electron with this periodic ion potential, okay? And that interaction modifies the wave function, and in turn modifies the mass of the electron, and that's why it's called the effective mass. The actual mass of the electron does not change, but when I capture the complicated interactions of the electron moving in this periodic ion potential, you can simplify the math and define a new effective mass which captures those interactions, okay? And that's given by this curvature of the band structure. I don't know if that was confusing. I'll come back to this again, like I said, next week when we start looking at electron and hole transport in a semiconductor, okay? So to repeat what I said, you know, these EK band structures come out of the solution of the Schrodinger equation. And as I was saying, the Schrodinger equation, you have to put in this periodic crystalline potential into the Schrodinger equation. And when you solve it, you'll get these wave functions, which are now no longer going to be plane waves, e to the power jkx, as we solved last week, but it'll be a plane wave multiplied by a new function, which also has the same periodicity as the crystal potential. And this plane wave multiplied by this new periodic function are called Bloch functions. Bloch with B-L-O-C-H, not B-L-O-C-K. Okay, Felix Bloch was a physicist who first solved this problem, and he won the Nobel Prize in physics for this. Okay, it basically, if you look at it, basically what he was doing was he was taking a Fourier transform of this periodic function, okay? And that's how you can come up with mathematical formula. All right, so we get two results, right? The first result is the velocity of a particle is given by 1 over h bar slope of d dk, and the mass of a particle is given by h bar squared divided by the curvature of these curves, d2e dk squared, okay? Now let's apply these equations to these band structures, okay, in the conduction and the valence band. Well, in the conduction band, I get a positive curvature, okay? That's what you get when you have the curving in a concave fashion like this. And therefore, the effective mass of electrons in the conduction band are going to be positive, okay? The velocities, as we just saw, increase as you move away from the origin. How about for the valence band? What is the curvature? Is it positive or negative? It's negative, right? Therefore, the electrons in the valence band behave as if they have a negative mass. So now things are getting really tricky, right? I mean, how can a particle have negative mass, negative effective mass? Well, the actual mass of the electron in the valence band is exactly the same as you have in free space. But once you take into account the interaction of the electrons in the valence band with this periodic crystalline potential, you can capture those complicated interactions with the effective mass, which turns out to be negative for the electrons in the valence band. All right. But instead of using the language of electrons, as I said, you're better off typically using the language of holes. Okay, let's see how that works out. So what I'm showing over here is an expression for the current density J. J is called current density and is given by current divided by the cross-sectional area for current flow A. Okay, so current density is current flowing through unit cross-section. If you wanted the actual current, it's just multiplied by the cross-sectional area. Okay. Now the current density in the valence band can be written as a sum of the current carried by each electron traveling with a velocity vi, right? And then if I'm looking at a certain volume v, per unit volume, it will be simply given by 1 over the volume of the crystal. Okay. Let's assume it's a unit cube. Everything is 1, 1, 1. So then v would be equal to 1. Okay. But if it's not, scale it up if you want current density. That's all that I'm saying. Okay. The key part is the summation term over here. So what I'm saying is to calculate the current due to all these electrons in the valence band, and now the valence band is not completely full, suppose it's partially full. The way you have to do that is you have to sum over the filled states, right? So certain states are filled up by electrons and they're traveling with a velocity v sub I. So you sum over the filled states, and to get the current, you have to multiply that by the charge of electron, which is minus q. Now, what is the velocity? Well, we just saw that velocity is equal to 1 over h bar dE dk, right? So for each of these electrons, I get the corresponding slopes, I get the corresponding velocities, right? Now, this sum over filled states can be written as sum over all the states in the valence band minus a sum over the empty states, right? So I'm writing the sum over filled states as sum over all the states minus sum over the empty states.
Do you already know the values for the empty states in all the states, or would that just be something you'd find out?
So you can calculate the velocities of the states, right? The velocities are given by the slopes at different locations. So that gives you the VIs for the ith electron, right? Now let's see what the summation over all the states would be. Well, these band structures are symmetric parabola. So you can clearly say that for every state, say at this location with a velocity like so, there'll be a corresponding mirror state with opposite velocity, right? Another state over here, it's a symmetric parabola, I'll have an opposite velocity, right? So what would the sum over all the states equal to?
Zero.
What?
Zero, wouldn't it cancel out?
Exactly, very good. Okay, so for every positive direction electron, you have a cancellation band, negative direction electron, right? So the first summation has to equal to 0. So I'm saying that the summation over the filled states is minus the summation over the empty states. So what happens then is this minus sign can cancel with this minus sign, And you can just as well write it as plus summation over empty states. Now charge becomes plus Q times VI. And that is what I say is a hole. So a hole is the unoccupied states and they behave like quasi particles with a positive charge. So that is the mathematical formulation of holes. Now you might say that, I believe in electrons, holes are a figment of your imagination, right? I mean, I want to do all my calculation in terms of electrons. You're welcome to do that, but then you'd have to do the summation over, roughly an Avogadro number of electronic states, right? Because there's an Avogadro number of electronic states in a crystal, minus maybe, I don't know, 15 states that are empty, right? There are 15 holes, right? Now, would you rather do a summation over 10 to the 23 minus 15 states, or just the 15 whole states? Clearly, it's much easier to work in terms of this few whole states, okay? So holes are particles with a positive charge, while the electrons, of course, are particles in the conduction band with a negative charge. Now, in the valence band, if I use the language of electrons, we end up getting a negative mass, as we just saw, because the curvature is negative. But if you flip to the language of holes, remember we said that the hole energies increase downward, but the electron energies increase upward, hole energies increase downwards. So if I work in the language of holes, the holes actually will have a positive mass, because the hole energies have the negative the increase downwards, so they have the opposite orientation as the electron energies. So in the language of holes, you can think of these quasi-particles with a positive charge and a positive mass. On the other hand, if you want to stick to the language of electrons, in the valence band, they will have a negative mass. Hopefully that wasn't too confusing. Any questions? So once again, please stare at that band diagram and make sure that you're very comfortable with what the axes are, what they mean, because you'll have homework problems on that. I will definitely give you exam problems where you have to analyze band diagrams, because all our device physics will be analyzed in terms of these simplified band diagrams. So the band structures we'll use once in a while, but the simplified band diagrams we'll be using all the time. Okay, so you have to be very, very comfortable with those.
When calculating the velocity of a hole, can we still use the 1 over h bar times d dk?
Yes.
It's the same for both electrons and holes. We don't have to.
Yes.
Okay.
Right.
Thank you.
Yeah. But the sign of the slope will be different, of course, right? Yeah. And it's
Right.
1 over d. It's 1 over d dk. We should have mentioned that. So I'm saying the velocity is equal to 1 over h bar dE dk. Now, what is E equal to? E is equal to h bar omega. So this is also same as d omega dk, where omega is the frequency in radians per second, and k, of course, is a wave vector, right? And if you remember your freshman physics, d omega dk is what's known as a group velocity of a group packet, okay, of a wave packet. So in other words, if I create a localized wave, okay, you do the Fourier transform, and it can be decomposed into various frequency components, omega, with different amplitudes, A1, A2, A3, etc. And this whole wave packet will travel with a group velocity, d omega dk, and that also is the same as 1 over h bar dE dk. Okay. When I was in undergrad, I always had trouble with this concept of group velocity, and it's a funny concept. You think of a wave with a certain velocity, but when you analyze a wave, you have a phase velocity and a group velocity. It's really the group velocity which is relevant in terms of how the wave packet moves and how much the velocity at which the energy carried by the wave is transported and things like that. But it's a little bit hard to grasp. So yeah, I always struggled with that. Okay, so let's move on. So we've now introduced a language of electrons and missing electrons or holes, and let's see how we can carry that analysis further. Okay, so in this figure, I'm showing the crystal structure of silicon, which in chapter 1 we saw is a diamond structure where every silicon atom is surrounded by 4 nearest neighbor silicon atoms. Now, I'm showing this in a 2-dimensional format. The actual structure, of course, is 3-dimensional. And to refresh your memory, the structure is a FCC crystal, a face-centered cubic crystal with a basis of 2 atoms, where the second atom in the basis is displaced from the first one by A/4, A/4, A/4 along the X, Y, Z axes, where A is the size of the cube or the lattice constant. Remember that? Well, if you did that exercise, as I said, you'd find that you'd end up with every silicon atom is now surrounded by 4 nearest neighbor silicon atoms having the same bond lengths and the same bond angles of 109 degrees, okay? And that's what the tetrahedral arrangement of atoms was, right? So in 3D, you have atoms at the apexes, and then you have an atom in the middle, and then you have these 4 covalent bonds. Here I'm showing it in a flattened out version in a 2-dimensional format. So every atom is surrounded by 4 nearest neighbor silicon atoms. And these double lines indicate these 4 covalent bonds made up of 2 electrons, one from, say, this atom, one from the neighboring atom, okay? And the nice thing is, by doing so, you see that, say, this silicon atom is surrounded effectively by 8 electrons. Therefore, that silicon atom becomes very happy because it has this stable octet of electrons. Similarly, the neighboring silicon atom also is surrounded by 4 nearest neighbor silicons. That's also happy, right? And that's what keeps the whole crystal in place by having this network of covalent bonds. Now, instead of silicon, if these atoms were carbon, that's what diamond looks like. That's why it's called the diamond structure. All right, now if all these covalent bonds were intact, if we apply electric field, there will be no electrical conduction because then all these electrons are tied up in covalent bonds. In the language of energy bands, which is what's shown on the left-hand side, that would mean I have the valence band, which is chock full of electrons, nothing missing, and the conduction band is completely empty. And as I said, using my water bottle analogy, if you apply electric field in this scenario, in the conduction band, which is completely empty, clearly there'll be no electrical conduction. I mean, that's easy to see. But in the valence band also, which is full of electrons, there'll also be no electrical conduction. And that's a little bit harder to see at first, okay? Because you say that, wait a minute, I mean, I got all these electrons in there. Why can't they respond to the electric field? The reason they cannot is if electron is to respond to electric fields, it has to gain energy or lose energy, right? But for it to gain or lose energy, you find that there's already another electron at that other state, right? And no 2 electrons can occupy a certain state because someone would be very unhappy. Anyone remember who that is?
Pauli.
Very good. Yeah, Pauli would turn in his grave. All right. So all the covalent bonds intact correspond to full bands and empty bands, okay? Now at room temperature, say 300 Kelvin, where kT, Boltzmann constant times temperature, is about 25 milli-electron volts, these electrons are jiggling around and a few of them might be shaken loose. If they're shaken loose, you end up with electrons which can now move around in the crystal. So if you have electric field, say, pointing to the right, these electrons with a negative charge, which way would they move? To the right or to the left?
To the left.
Very good. And the holes, what's left behind is the missing state. That's my hole. Which way would that move? To the right, right? So this broken bond in the band language corresponds to exciting electron from the valence to the conduction band, okay? Now, if I increase the temperature, what do you think happens to these numbers of electrons and holes? Do they stay the same or increase or decrease, you think?
Increase.
Very good. In fact, we'll see it increases exponentially with temperature. It'll be increasing as e to the power minus the band gap divided by 2 kT. We'll prove that next week, okay? Now at room temperature, in a pure semiconductor, the number of electrons and holes obviously have to be equal to each other, right? Because if you break a bond, N equals P, and they're both equal to what I call my intrinsic carrier concentration. So at room temperature in silicon, Ni happens to be about 10 to the 10 electron hole pairs per centimeter cubed. That's the number of electrons or holes that we have in pure silicon at room temperature. Okay, that's called the intrinsic carrier concentration N sub I. Now, to make semiconductor devices, you cannot work with just pure semiconductors. You have to engineer different regions and make them more electron rich or N type, or hole rich or P type for positive or negative conduction. Okay. And the way you do that, we already mentioned that in passing when we introduced semiconductors in chapter 1. We do that by introducing impurities purposely, known as dopants. Okay. Now, what kind of impurities? Well, silicon, you may recall, is in column 4 of the periodic table. The column tells you, the number of the column tells you how many electrons you have in the valence shell. Silicon is in column 4, therefore it has 4 electrons in the valence shell. Arsenic or phosphorus lie in column 5. So what do you think would happen if I replace a silicon atom with an arsenic, as shown over here, which has 5 electrons? Well, what we find is 4 of those 5 electrons go towards satisfying these 4 covalent bonds, but then the 5th one, there's no place for it to fit, right? So that is donated to the crystal. That's why arsenic is known as a donor type impurity. It's donated to the crystal, okay? And arsenic is known as a donor type impurity, okay? And that will give rise to a conduction electron. Now, the arsenic to begin with was a neutral atom. If it gives off electron which can now roam around in the crystal and respond to electric fields, you know, if I had electric field like so, it moves opposite to the electric field. What's left behind is an arsenic ion, right? What do you think is the charged state of the arsenic? Is it still neutral or is it charged?
Charged.
Charged. It'll become positively charged, right? So donor, when it ionizes, becomes positively charged. Now notice the total charge is still 0, right? Because the positive charge of the donor is balanced by the negative charge of the electron, which roams around. So the total charge, which is known as space charge, is neutral. This is a concept called space charge neutrality. But the two charges are different in the sense that the electron can move around and respond to electric fields. But how about the positive ion, arsenic ion? If I apply electric field pointing to the left, you think the ion, which is positively charged, could move in this direction?
No.
No, because it is locked in the lattice, right? So the donor type impurities are boron, which I'll talk about, acceptor type impurities are locked in the lattice. They'll give rise to what we'll call space charges in a p-n junction, for example. The things that can move around are the electrons and the holes, okay? So when I introduce this impurity in the energy band diagram, what ends up happening is you introduce an energy level close to the conduction band in the band gap. Now you might say, wait a minute, I thought you said that a band gap has no allowed quantum states. Well, that's true only if it's a perfectly pure, defect-free semiconductor or a solid. If I introduce impurities or if I introduce other kinds of structural defects, all bets are off and you can have energy states in the band gap. And in the case of donors, those energy states happen to lie close to EC, the bottom of the conduction band. How close? Well, the magnitude of the energy gap in silicon is 1.1 eV. The spacing in energy over here is maybe about 50 to 100 MeV, million milli-electron volts. So it's very, very close, okay? Notice it's kind of comparable to KT, which is 25 milli-electron volts. So because that energy separation is so small, this 5th electron can very easily be excited into the crystal. So as shown at 0 Kelvin, absolute 0, it's still locked in the arsenic ion, arsenic atom. So this electron is not donated, but any finite temperature, say 50 Kelvin or certainly by 300 Kelvin room temperature, it's excited in the conduction band, okay? So you can describe the same physics either in the language of chemical bonds, that's called the bond picture, or energy bands, okay? So it's the same physics, but described in slightly different language. Now, once I've understood what happens with column 5, donor type impurities, column 3 is easy to understand. That's called an acceptor type impurity. So boron in column 3 has 3 electrons. It can satisfy 3 of these covalent bonds, but when it comes to the 4th one, there's a missing state. Therefore, that acts like a hole. So what will happen is the boron will like to grab an electron from somewhere. that's called accepting. It's a polite term for stealing an electron from somewhere, okay? And likes to form this covalent bond, say. In the process, it becomes a boron minus, accept impurity. But if I steal electron, where has the hole moved? So the hole moves over there, right? Similarly, this electron from this band might move over there, or the hole moves in this direction, okay? So you can describe the language either with holes or with electrons, okay? So here you introduce an energy level close to the valence band, and at finite temperature, these electrons in the valence band, full valence band, can be excited, okay? And what's left behind are these positive holes, okay? On the other hand, if you cool the semiconductor down to very, very low temperatures, maybe not absolute Kelvin, maybe a few Kelvin, KT becomes smaller and smaller and smaller, and these electrons drop back over here. And similarly, these holes, the electrons drop back. So that phenomenon is known as carrier freeze out. Now, based on your intuition, do you think a semiconductor device would operate properly if I was at such low temperatures that the carriers freeze out?
No?
Is that
No.
a question?
Yeah, that was a question, and then someone gave the right answer. It would not, okay? So if you take your microprocessor and you dunk it in, liquid nitrogen or liquid helium, you'll find that they stop working, okay? Because the carriers will freeze out. Conversely, what do you think would happen as I keep increasing the temperature? At room
Wouldn't the
temperature, you
same
typically
apply?
get what?
Wouldn't the same apply if you go above the room temperature because it's exciting the electrons and it's changing the properties?
Right. So that's absolutely right. But what happens if I keep increasing it, not just a little bit, but a lot? Remember the other process that we mentioned in terms of
Wouldn't they
intrinsic
just
carrier
start
function?
breaking bonds? And so they
Exactly. Right. So in addition to the electrons that are donated by the donors or the holes created by the acceptors, I can now start getting more and more direct excitation from the valence to the conduction band, right? So the Ni, the intrinsic part, keeps increasing. And if Ni increases to the point that it swarms whatever the donors or the acceptors are doing, once again, the devices would fail. So all semiconductor devices operate only in a finite temperature window. If you make it too cold, carriers freeze out. If you make it too hot, the thermal excitation of intrinsic carriers swarms out the doping effects, and the devices will fail also. Okay?
I have a couple of questions.
Sure.
So in this particular crystal, you have the arsenic with the free electron and then the boron with the hole. Would that
Mhm.
electron from the arsenic create a covalent bond between the boron and the silicon?
That's a very good question. So I was going to come to that later on. So now, if the two are very, very far apart, now you can't really form a bond like that. But you're absolutely right. This electron created by the arsenic can recombine with the hole created by the boron. And that phenomenon is called doping compensation. So what you'd end up getting is a net doping, which would be the difference of the arsenic concentration minus the boron concentration. Or if we had more boron, it would be the boron minus the arsenic. So there's a cancellation effect. Very good. Okay, and that phenomenon is called doping compensation that we'll work on some math problems next week. Okay.
I had one more question, if that's fine.
Sure. Yeah, sure.
So we're talking about here at absolute zero, the semiconductor wouldn't really work, but superconductors with metals, when they're cooled to absolute zero, then they have like zero electrical resistance. So why are they two opposite ends of the spectrum?
That's an excellent question also. So not everything becomes a superconductor, okay? For superconductors, it's totally different physics. What ends up happening is you have pairs of electrons with opposite spin. So you have an electron, say, with the spin up, forming a pair with another electron with spin down. And these are called Cooper pairs, after physicist Cooper, okay? And once you form these Cooper pairs, they convert into bosons. Remember we said that electrons have spin half, right? And those are fermions. Now, if I have two halves, what is the spin of the whole thing? Well, if they're in opposite directions, it'll either be 0 or 1, depending on whether they're in the same direction or not, right? The point is, in a pair, you get integer spins, while in fermions, individual electrons, you have half spins, okay? Now, once you form these bosons, they can form what's called a Bose-Einstein condensate, okay? And that's what you have in a superconductor, okay? And under those conditions, it can travel as a superfluid with zero resistance. So it's different physics. Tell you what, in the next class, when I start discussing Fermi-Dirac statistics for fermions and Bose-Einstein statistics, I'll mention this again briefly, okay?
Okay, thanks.
Yeah, these are all great questions. All right, so what I want to do next is, I just mentioned that these energy levels for the donors and acceptors are so-called shallow in the sense that they're either close to EC or slightly above EV. That's what the term shallow means. By contrast, if you have a deep level impurity, those would introduce energy levels near the middle of the gap. Maybe not exactly the middle, but close to the middle. Those are called deep. So shallow means either close to the valence bandage or the conduction bandage, while deep means near the middle of the gap. Generally speaking, deep level impurities we'll see as you get into devices are bad because that can mess up things like, now electrons in the valence, in the conduction band can fall into the so-called deep trap. This is sometimes called traps, okay? And can recombine with holes in the valence band. All kinds of nasty things can happen. So in general, deep level impurities are bad. Shallow impurities, if you design them at the right concentrations, at the right locations, that's how you make all your semiconductor devices, such as PN junctions. Now you then implant acceptors in one region, and right next to that you implant donors, and that's how you make a PN junction diode, for example. Okay. All right. So in the next slide, I go through a hand waving type calculation for these energy levels of the donors or acceptors. Okay. And this is known as the hydrogenic model, because this is really the Bohr model of the hydrogen atom that people steal and just change the parameters. Okay. Now you can go back to chapter 2 later on, and you can see what Bohr did when he looked at the electron orbiting around the hydrogen nucleus, right? And he come up with these discrete energy levels, right? Where you get E sub n equal to the Rydberg energy, which is minus 13.6 divided by n squared. Now, if you look at this expression, you'll see that you have terms involving the mass of the electron and the dielectric constant of the electron. All that you do is you take the same model, and wherever you have the mass, you replace that by the effective mass of electron in the semiconductor. Okay. And once again, effective mass is capturing the interaction of the electron with this periodic crystalline potential. So that's captured in this nice number, which is why it's called the effective mass. The actual mass of the electron does not change. Similarly, wherever I have the free space dielectric constant, I have to replace that by the relative dielectric constant of the semiconductor. Okay. So if we put those in, so for the ground state in hydrogen, that's 13.6 electron volts, you find that for most semiconductors, the effective mass is about 1/10 of the actual mass, approximately. This is just back of the envelope type estimates. Similarly, the dielectric constant in semiconductors, the relative dielectric constant is roughly a factor of 10 or so. Once again, depends on the exact semiconductor. We're just doing a ballpark back of the envelope estimate. So what you get is something of the order of 10 electron volts times 0.1 divided by 10 squared. Okay, so by putting those numbers in, you end up getting these binding energies of donors, say. So this is phosphorus donor impurity. The binding energies work out to about 10 to 100 millielectron volts, and that's indeed the case. Similarly, in the Bohr model, you had an expression for the radius, Bohr radius, once again in terms of mass and the dielectric constant of free space, that is half an angstrom. You can plug in similar effective masses and actual dielectric constant, and you get a modified Bohr radius, which should work out to about 50 angstroms or so. All right. And that's an interesting number because lattice constants in silicon are 5.43 angstroms. I mean, that's not the nearest neighbor distance. That was the size of the FCC cube. The nearest neighbor distance is actually even less. It's about 2.3 angstroms. Okay. So we did this calculations in chapter 1. But the important point is this number is much, much larger than the lattice constant, meaning that this electron is really orbiting over many, many lattice constants, meaning that it's not really bound to the phosphorus donor impurity anymore. It's essentially free to roam around in the crystal. So the point is, these energy levels indeed show that they're shallow donors, and they're not really, these electrons are not really tightly bound to the donor. So what's shown in this figure down below is for silicon, the energy levels that are introduced in the band gap for different kinds of impurities. So you have the shallow donors, phosphorus and arsenic, and notice the energies, these are electron volts. that's millielectron volts. So that's 49 millielectron volts. That's 44 millielectron volts. So that's in the right ballpark. The slight differences that you see are because, you know, a phosphorus nucleus is obviously different from an arsenic nucleus. So those introduce second order corrections. Those are called central cell corrections. Boron shallow acceptor, 45 millielectron volts above the valence band. Okay. Other column 3 impurities over here. On the other hand, if you introduce impurities such as gold into a silicon crystal, are these shallow or deep? They're deep, right? And therefore they act as electron or hole traps. So if you work at, say, Intel or Samsung and you accidentally introduce gold into the semiconductor factory, into the wafers, they'll take you out into the parking lot and shoot you on the spot.
What's the difference between a shallow and a deep hole?
So a shallow impurity is close either to the conduction band edge or the valence band edge, okay? While a deep level trap is very far away from either of these band edges. It's near the middle of the gap.
Do we have like a set value range for that, or is it just?
No, it's a gradation, okay? So the more I go towards this, it becomes deeper and deeper, okay? It's called deeper in the sense that if you have an energy level like this, and suppose it was a donor type impurity, say column, sulfur is a good example, okay? Sulfur is in column 6 of the periodic table. So in principle, you could have donated those 2 electrons into the conduction band, right? Just like we did for the 1 electron in the arsenic or the phosphorus, right? But because these energy levels are so much deeper, what do you think is the excitation probability going to be? Large or small? It's going to be very, very small, right? So these electrons in sulfur will not be ionized. That's why they're called deep, okay? While these are shallow, these traps created by arsenic or the phosphorus are very, very shallow, so they can be excited into the conduction band. On the other hand, for sulfur, these energy levels are way, way down below. So for them to be excited in the conduction band takes a lot of energy, and that's not going to be very likely. Okay. All right. Now, so far we have said that the band structures, now we are looking at energy not as a function of position, but rather as a function of the wave vector k, which is basically proportional to the velocity or the momentum of the electron. We said that it's a parabola for the conduction band and an inverted parabola in the valence band, okay? And the figures so far had the minima or the maxima both had k equal to 0, okay? Not all semiconductors will have that kind of a band structure, but if they do, those are called direct band gap semiconductors. In many cases, however, we find that the minimum in the conduction band will be offset from k equal to 0, as shown on the right-hand side. Those are called indirect band gap semiconductors. Okay, and that has very, very important implications, not so much for electronics, but for optoelectronics, devices like semiconductor lasers or light-emitting diodes, photodetectors, et cetera, okay? And let's see why that is. So in the case of a direct semiconductor, you can have a transition from the valence to the conduction band by simply absorbing or emitting a photon. Remember we said that if the photon has an energy greater than or equal to the band gap, it can be absorbed, and electron from the valence to the conduction band can be excited, creating electron hole pair, okay? Now in this process, you'll notice that I'm not changing the k value that much, right? It's a vertical transition, meaning that the momentum doesn't change a whole lot, okay? Momentum of the electron, only the electron energy is increasing, right? And that's good because for visible wavelengths, you can work out the momentum of a photon momentum, which is h divided by the de Broglie wavelength, okay? In the visible range from red to blue, red has a wavelength of 8,000 angstroms, blue is 4,000 angstroms. Bottom line is, if you plug in those typical wavelengths of photons, you find that the momentum of a photon is very, very small, okay? And therefore, in this process, where you have to satisfy both energy and momentum conservation, a direct bandgap semiconductor can absorb a photon very effectively, or it can emit a photon by recombining electron with a hole. On the other hand, if I had a semiconductor with this sort of a band structure, which is indirect, notice I have a problem, because electron at that location has a different value of K than an electron at that location, right? So therefore, for a transition from the valence to the conduction band or otherwise, you have to change not only the energy, but you also need a significant change of momentum, which a photon in the visible range does not have. So for a process in an indirect semiconductor, you have to involve not only a photon, which can carry a lot of energy, but also a so-called phonon, which is a quanta of lattice vibration. I don't know if you remember, I introduced the term before. We said that in an atom, you can imagine these atoms has been connected by imaginary springs. You don't really have springs in a crystal, of course. These are these interatomic forces, which can be modeled by these imaginary springs. But then these atoms are not going to be static. At room temperature, they'll also vibrate about some equilibrium location. And that creates elastic waves, which propagate in the crystal. And just like all waves, these elastic waves are also quantized, and they're subject to the same Planck relationship, E phonon equal to h bar omega of the phonon, and momentum of the phonon equals h over the wavelength of the sound waves or the elastic waves, okay? Now, it turns out if you plug in the magnitude of wavelengths of phonons, the wavelengths correspond to roughly something of the order of the lattice constant, say a few angstroms. So now for the momentum, you get h over something of the order of say 1 angstrom, while for the photons in the visible wavelength range, you get something of the order of thousands of angstroms, okay? So for phonons, they can carry a lot of momentum, but it turns out if you look at the energy of the phonon, those are very, very small compared to photon energies, okay? So what I'm trying to say is, in the case of indirect band structures, the processes of transition are more complicated than in direct bandgap semiconductors. Because in an indirect semiconductor, you have to invoke both a photon as well as a phonon to do these processes. And as such, they're not as effective. So what one finds is if I want to make an optoelectronic device, such as a semiconductor laser or an LED, I choose direct semiconductors, such as gallium arsenide. On the other hand, silicon, unfortunately, is an indirect bandgap semiconductor. So while it's perfectly adequate for making electronic devices, such as diodes or transistors, you cannot make the lasers in silicon, okay? If you could, you'd be rich and famous, all right? So in the next slide, I put some numbers to quantify the momentum and energy of a photon versus the momentum and energy of a phonon, okay? Phonon is a particle of sound, photon is a particle of light. So the way you do that is to use the Planck relationship and the de Broglie relationship, and I've already kind of given you the answer. So for photons, we know that the frequency and wavelength, the product of the two, is a constant. That's the speed of light, okay? The de Broglie wavelength is given by h over momentum, or momentum is given by h over lambda. If I look at the visible part of the electromagnetic spectrum, as I said, the electromagnetic spectrum is very, very broad, of course. But then you have red, blue. On this side, you have infrared, okay? And then you have radio waves and all that, longer and longer wavelengths. So wavelengths increase this way. Wavelengths decreasing this way. Over here, you'll have ultraviolet, all the way up to X-rays and gamma rays and things like that, okay? So if you go to the right, the photon wavelengths increase, and therefore the momenta decrease. Now, as the photon wavelengths increase, what happens to the frequency? The frequency decreases, therefore the energy also decreases, right? So these longer wavelength photons have lower photon energies as well as less momenta, okay? If you move this direction, the photon packets of energy carry more punch, okay? They have more energy and more momentum. As I just said, if you concentrate on the visible part of the spectrum, which is the most relevant because if I'm going to make a laser or an LED, generally speaking, I'm not interested in making a laser which operates in the infrared, say, right? I mean, sometimes you do, but in most cases for optoelectronic devices, you want light that you can see with the human eye, right? So generally speaking, the blue to the red part of the spectrum is what's relevant for most optoelectronic devices. Not all. I mean, you can have optoelectronic devices in the UV and the IR also, but the visible part of the spectrum is the most relevant. And there we said the momentum works out to be very, very small, while the energy, if you plug in the numbers of corresponding frequencies, you get something of the order of electron volt. So going back to the band gap, remember we said that typical semiconductor band gaps are of the order of electron volt. Therefore, the photons carry enough energy to go from the valence to the conduction band. On the other hand, the momenta is very, very small on this scale. Okay. Now, although I have not described that, it turns out this scale of momenta happens to be of the order of h over the lattice constant A. Okay, I haven't proven that. Okay, if you take a graduate course, you'll find that the extent of the momenta that you have in these band structures is approximately of that order. Okay, and that spacing in K space is known as your Brillouin zone, after a French physicist who did this sort of analysis of propagation of waves in a crystal. Okay, let's not worry about the details. The important point is the magnitude of the variation of momenta is of the order of h over A being the lattice constant. Lattice constant is of the order of angstroms. Okay, so on that scale, the photon hardly has any momenta, but it has a lot of energy. On the other hand, the phonons, because those are vibrations of these atoms, which have a spacing of a lattice constant, they do carry a lot of momenta on this energy scale. Okay. On the other hand, if you look at the energy of the photons, that's given by h nu. If you go through the math, that works out to of the order of kT, the thermal energy. I'm just stating this. I'm not proving any of this, unfortunately. So that will work out to be of the order of the thermal energy kT, which is about 25 millielectron volts. Okay. Why is that? That's because these phonons, as I said, correspond to these random thermal vibrations of the atoms, and thermal vibrations of particles, electrons or atoms or whatever, will have a kinetic energy of the order of kT. Once again, this is K Boltzmann times T. That's different from this wave vector K. Okay. So that may have been a confusing discussion. Just remember the punchline. Direct bandgap semiconductors have the conduction band minimum at the same value of K as a valence band maximum. And those semiconductors are going to be very effective for optoelectronic devices, which either absorb photons or emit photons, where the photons carry a lot of energy, but hardly cause any change of momenta. For indirect semiconductors, you have to involve not only a change of energy, which the photons can provide, but also a change of momenta, for which you need phonons. So these are more complex processes involving photons plus phonons, and therefore they're not as effective for optoelectronic devices. That's really all that you need to remember for this class, okay? And we'll revisit this at the very end of the course in chapter 8, when you look at optoelectronic devices like lasers, et cetera, et cetera. Okay. All right, so as I said, semiconductor band structures belong to those two broad categories. Now let's look at actual band structures of real semiconductors, silicon and gallium arsenide, okay? So what you'll notice immediately is that, gosh, these are getting pretty complicated, right? I mean, I have all kinds of curves, but if you get over your initial shock, hopefully you'll see that it kind of looks like a parabola, right? So I'm plotting energy increasing upwards for electrons as a function of the wave vector K, okay? I'll go over this again next week. This is just a preview, okay? So here I'm looking at wave vectors in different directions in the crystal. But roughly speaking, you see that you have parabolic shapes, right? Here and there. Similarly, in gallium arsenide, valence band, conduction band. Question for you. If I wanted to make a semiconductor laser based on what I just told you, would I want to make it in silicon or gallium arsenide?
Gallium arsenide.
Gallium.
Yeah, very good, because it's a direct bandgap semiconductor, okay? Now, let me also ask you, remember I said that the mass of the electron is given by the effective mass, not the actual mass. The actual mass is always the same. Effective mass is given by h bar squared divided by the second derivative of the curvature. So just by staring at these two conduction band age minima, if I wanted to make faster transistors, which semiconductor thing do you think would be better? A faster transistor would involve lighter mass electrons because they could move in a more agile fashion, right? So just by looking at the band structure, can you guess which would be a faster transistor?
Does negative mass count as a faster transistor or
Well, no, you should look at the magnitude of the mass, right? Because negative mass means for the holes, right? So negative mass is for the electron negative masses, but then if you shift over to the hole language, since the whole energy is increased downwards, the holes have a positive mass, okay? So just look at the magnitude of the curvature. Which has let's concentrate on the conduction band. Which one do you think has a sharper curvature?
Silicon?
So sharper curvature would be something like this. A gentle curvature is something like this, right? So is this sharper or this sharper? Gallium arsenide.
looks like
Gallium arsenide is sharper over here, okay? So gallium arsenide electrons have a lower effective mass, and in principle, you could make faster transistors in gallium arsenide than in silicon, okay? So why aren't all microprocessors made in gallium arsenide? Well, it turns out there's a lot of technological issues that we'll describe in chapters 4, 5, and 6, okay? We'll start off with this. There's a lot of information in this figure, and we'll also go into a more detailed analysis of this band diagrams, simplified band diagrams, and look at this, interaction between with electric fields and how you have transformation from kinetic to potential energy and all that. I've already told you this, but because they're so important, I'll repeat that again next week. Okay? Any questions? All right. See you next week.